Io, one of Jupiter's largest moons, has long captured the attention of scientists, but the recent discoveries made by the James Webb Space Telescope have expanded that interest even further. Known as the most volcanic world in the solar system, Io is a place of constant geological activity. However, JWST has identified vast regions of intense heat, areas of molten rock, and unusual chemical patterns that provide new insight into how Io's volcanic systems operate. So, how can powerful geological forces influence other planetary bodies throughout the solar system? Before we begin, let us know in the comments below where in the world you're watching from, and what time it is there now. And if you enjoy learning about space, consider subscribing. It really helps us keep making more content like this. In the winter of the year 1610, the quiet skies above the Italian city of Padua witnessed one of the greatest turning points in human history. A man named Galileo Galilei stood on a rooftop, leaning over a simple telescope that he had built with his own hands. By modern standards, it was an unimpressive device, a narrow wooden tube fitted with a few glass lenses, but in Galileo's hands it became something extraordinary. It became a window into a universe that no one had ever truly seen before. That cold January night, Galileo aimed his handmade telescope toward the giant planet Jupiter. As he focused his trembling hands and sharp eyes, he noticed something unexpected: tiny points of light close to the planet. At first, he thought they were distant stars that just happened to lie near Jupiter in the sky. But night after night he kept watching, and the mystery deepened. These little lights did not stay still as stars were supposed to. They shifted positions, sometimes vanishing behind Jupiter and then reappearing on the other side. Galileo grew curious and began recording their movements in his small notebook, sketching their positions carefully each night. Soon, a pattern emerged. These lights were not stars at all. They were moving around Jupiter. What Galileo had found was astonishing: moons orbiting another planet. For the first time in human history, someone had seen worlds circling something other than Earth. Today, we know these moons as Io, Europa, Ganymede, and Callisto, the Galilean moons named in his honour. Io, the closest to Jupiter, was the first of them. Though it may seem a small discovery now, in 1610 it was nothing short of revolutionary. At that time, most people in Europe believed in an Earth-centred universe, an idea that came from the ancient Greek philosopher Aristotle, and was later reinforced by the teachings of the Catholic Church. The Earth, they said, stood still at the centre of everything, while the sun, stars, and all the planets moved around it in perfect circles. But Galileo's discovery challenged that belief. Here was visible proof that not everything revolved around Earth. The tiny moving lights orbiting Jupiter showed that there were other centres of motion in the cosmos. If Jupiter could have moons, then perhaps Earth was not the centre after all. Maybe it too moved around the sun. Such ideas were dangerous in Galileo's time, but he refused to stay silent. Only a few months after his first observation, Galileo published a small book in Latin titled Sidereus Nuncius, or the Starry Messenger. In it, he described his findings in detail, how he had seen the moons, how they moved, and what that meant for our understanding of the universe. The book caused an immediate sensation across Europe. Scholars, priests, and philosophers argued fiercely over its meaning. Some refused to believe it. Others rushed to test it for themselves, building telescopes and turning them toward Jupiter. The moons were there for anyone brave enough to look. Those 4 faint points of light, no bigger than stars through Galileo's telescope, carried a weight far beyond their size. They shattered more than 1,000 years of belief in an Earth-centred cosmos and hinted at a universe far larger and more complex than anyone had imagined. Centuries later, spacecraft and modern telescopes would reveal Io as a restless world of fire and motion, alive with volcanoes and molten rock, a sight far beyond Galileo's dreams. But on that cold January night, all he saw was a single point of light circling Jupiter. From that simple observation, humanity's view of the universe began to change forever. When it came time to name his discovery, Galileo made a practical and political choice. In March of 1610, just 2 months after his observations, he published the Starry Messenger and referred to the moons not as moons, but as the Medicean stars, Sidera Medicea in Latin. The name was not chosen for scientific reasons, but for strategy. Galileo was hoping to win the favour of one of Italy's most powerful families, the Medici, who ruled Florence and influenced much of Europe. In a letter to Cosimo II de' Medici, the Grand Duke of Tuscany, Galileo offered to name the 4 new stars after Cosimo and his brothers. The gesture worked. The Medici were delighted, and Galileo was soon appointed as the court mathematician and philosopher in Florence. For a while, the name Medicean stars appeared in books, letters, and star charts, a symbol of both discovery and ambition. However, not everyone accepted this name. Outside Italy, many astronomers found it unsuitable. The German astronomer Johannes Kepler argued that the objects clearly were not stars at all. They moved around Jupiter just as Earth's moon moved around Earth. He and others preferred to call them moons or satellites, though the idea of planets having their own moons was still new and strange. Over time, the Medici name faded, and the moons came to be known by the names we use today: Io, Europa, Ganymede, and Callisto. What began as faint points of light in Galileo's modest telescope turned into one of the greatest discoveries in science. Those 4 little worlds proved that the heavens were not as fixed or simple as once believed. They showed that Earth was just one planet among many, and that the universe was vast, dynamic, and filled with endless possibilities. In the year 1614, a German astronomer named Simon Marius published a book titled Mundus Jovialis, which means the Jovian world. In that book, Marius boldly claimed that he had discovered the moons of Jupiter at the very same time as Galileo Galilei. This statement immediately stirred controversy. Galileo firmly rejected Marius's claim, insisting that the discovery was entirely his own. Despite the dispute, there was one part of Marius's work that endured: the names he gave to those moons. Marius was deeply inspired by classical mythology. Drawing from the ancient stories of Greece, he named the 4 moons Io, Europa, Ganymede, and Callisto. In Greek mythology, all 4 were known as companions or lovers of Zeus, who was the Greek counterpart of Jupiter. The choice made perfect sense. The moons revolved around Jupiter just as, in myth, these figures revolved around Zeus. Marius later explained that he got the idea for the names from another famous astronomer, Johannes Kepler, who had suggested naming the new satellites after Jupiter's mythical attendants. Marius liked the idea and decided to put it into practice. In his writings, he described Io as the closest of the 4 moons, followed by Europa, Ganymede, and Callisto. He even tried to calculate their distances from Jupiter and their orbital periods. Considering the simple tools he had available, his estimates were impressively close to what we know today. However, Galileo was not pleased. He saw Marius as a copycat trying to steal recognition for his discovery. For many years, Galileo and his supporters refused to use Marius's mythological names. Instead, they referred to the moons as the Medicean stars, a name chosen by Galileo himself to honour his patrons, the powerful Medici family of Florence. This disagreement divided the astronomy community. Some astronomers followed Galileo and continued to use the Medicean names, while others preferred the poetic and logical names suggested by Marius. Gradually, the mythological names began to take hold. They were simpler, more consistent, and fit neatly into the growing tradition of naming celestial bodies after figures from ancient myths. By the 18th and 19th centuries, the names Io, Europa, Ganymede, and Callisto had become the standard in astronomy books and star charts. It is interesting to note that the name Io did not come from Galileo at all, but from this later effort to give order and symbolism to the solar system. In Greek mythology, Io was a priestess of the goddess Hera who caught the attention of Zeus. To hide her from Hera's anger, Zeus turned Io into a cow and sent her wandering across the earth, endlessly tormented by a stinging gadfly. Her story is one of transformation, pursuit, and endurance, elements that strangely echo the real Io, a moon constantly reshaped by volcanic fire and ceaseless motion. In the end, the myth and the moon share a common spirit of restlessness, making the ancient name an unexpectedly perfect choice for one of Jupiter's most extraordinary worlds. The story of how Io got its name is a fascinating reflection of how astronomy itself has evolved over time. When Galileo first looked through his telescope in the year 1610, he simply noted the moons of Jupiter as small points of light, marking them with numbers and symbols in his notebook. Back then, the idea of giving these distant worlds names was still new. In those early days, names in astronomy were often chosen to honour powerful rulers or to win favour with patrons who supported scientific work. As time passed, however, astronomers began to see a need for more organised systems. They started naming celestial objects in ways that showed their place within the larger structure of the solar system. The moons of Jupiter, for example, became part of a grander naming pattern inspired by mythology, linking science with stories from the ancient world. Eventually, this simple act of naming became something much deeper. It shaped the way people thought about these faraway bodies, not just as distant points of light moving through the night sky, but as real worlds with their own identities, stories, and natural powers. Io's journey from being a nameless dot in Galileo's notebook to a world of volcanic fury and mythological wonder mirrors the human journey of discovery itself, from curiosity and observation to imagination and understanding. By the middle of the 17th century, the little moon called Io had already changed how people thought about the universe. It was no longer just a mysterious light circling Jupiter. It had become a real world, one that moved in a pattern that could be followed, timed, and predicted. And from those predictable movements came one of the most extraordinary discoveries in the history of science, the measurement of the speed of light. In the year 1676, a Danish astronomer named Ole Rømer was living in Paris, working at the Royal Observatory. His job was to make clocks more accurate and to improve predictions of eclipses, those moments when one celestial body passes in front of another. One of the best ways to test his calculations was by observing the moons of Jupiter, especially Io. Io was perfect for this kind of work. It moved very quickly around Jupiter, completing one full orbit in about 42.5 hours, just under 2 days. That meant every couple of days Io slipped behind Jupiter and disappeared into its shadow, only to reappear again on the other side. For astronomers of that time, these regular eclipses were like a dependable ticking clock in the sky. Unlike the rare and unpredictable lunar eclipses seen from Earth, Io's eclipses happened often and could be tracked precisely. But as Rømer continued to observe Io, he noticed something unusual. When the Earth was moving closer to Jupiter in its yearly orbit around the Sun, Io's eclipses seemed to occur a few minutes earlier than predicted. And when the Earth was moving away from Jupiter, those same eclipses appeared a few minutes late. The difference wasn't huge, usually between 10 and 15 minutes, but it was far too large to ignore. Io's orbit couldn't be changing that much. Jupiter's gravity was too powerful and steady to allow such variations. So Rømer decided to investigate more carefully. Over many months, he compared dozens of Io's eclipses, writing down the exact times and checking Earth's position in its orbit each time. The more he studied, the clearer it became that the timing differences weren't coming from Io or Jupiter. Something else was causing them. Then Rømer had a bold and revolutionary thought. What if the delay wasn't in the motion of the moon, but in the light itself? Most scientists at the time believed that light moved instantaneously, that when you lit a lantern or looked at the stars, the light appeared the moment it was produced. But Rømer's careful records didn't fit that idea. The only explanation that made sense was that light took time to travel, and that it moved at a finite speed. Rømer proposed that as Earth moved farther away from Jupiter, the light from Io's eclipses needed more time to reach us. The greater the distance, the longer the delay. That would make the eclipses appear later than expected. And when Earth moved closer to Jupiter, the light had less distance to travel, so the eclipses appeared earlier. In September of 1676, Rømer made his discovery public. He boldly announced that on November the 9th of that same year, Io would emerge from behind Jupiter about 10 minutes later than predicted. He explained that this wasn't because Io was late, but because the light from the eclipse took longer to reach Earth as the two planets moved farther apart. When the night of November the 9th arrived, his prediction proved exactly right. Io appeared 10 minutes late, just as Rømer had said it would. It was the first time in human history that anyone had used astronomical observation to show that light travels at a measurable speed. Although Rømer couldn't calculate the exact value of that speed with the instruments available at the time, he made an impressive estimate. He calculated that light would take about 22 minutes to cross the entire diameter of Earth's orbit around the Sun. Modern measurements show that the real time is about 16 to 17 minutes, remarkably close for a 17th century observation. The Dutch physicist Christian Huygens built upon Ole Rømer's work, using the Danish astronomer's careful timing and a bit of geometry to make one of the first direct estimates of the speed of light. Other scientists soon followed, armed with better instruments and longer measuring distances, but the real foundation had already been laid. Rumour had done something no one had managed before. He proved that light does not travel instantaneously. Using nothing more than his observations of a small, distant moon, he demonstrated that even light takes time to move across space. It is easy today to forget how revolutionary that idea was in the 17th century. Before Rumour, few people imagined that celestial events could be used to uncover the laws of nature. Yet Rumour saw what others missed, that light could be measured in time, and that timing itself could reveal its hidden behaviour. By linking that timing to something as regular and dependable as a moon's orbit, he turned the unseen into something that could be observed and calculated. Even more remarkable was how he achieved all this without any of the tools we take for granted today. There were no atomic clocks, no computers, and no advanced telescopes. Everything was done by hand. Rumour relied on simple mechanical clocks, early telescopes, and his own determination. He spent months watching the sky, recording tiny changes in Io's movements and matching them with Earth's changing position in its orbit. What seemed like a small, puzzling delay in Io's eclipses turned out to be a key to understanding one of nature's greatest mysteries, the finite speed of light. Rumour's discovery didn't just stop there. The timing of Io's eclipses became a vital tool in astronomy for many years afterward. For a time, they were even used as a kind of natural clock to help determine longitude on Earth. Before ships had accurate timepieces, some navigators tried to use Jupiter's moons to find their position at sea. If an eclipse of Io was predicted to occur at a specific moment in Paris, and you observed it happening earlier or later from your location, you could calculate how far east or west you were. It was a difficult and imperfect method, but it showed once again how valuable Io's regular motion could be. Today, scientists can measure the speed of light with extreme precision, using lasers, atomic clocks, and satellites. But none of that would have been possible without that first step, a distant moon orbiting Jupiter, disappearing and reappearing like clockwork. Those faint flickers of light were the earliest hints that something profound was waiting to be discovered. For a long time after Rumour's work, Io remained a mystery. Throughout the 18th and 19th centuries, telescopes were simply not powerful enough to show its surface clearly. Astronomers could only watch it glide behind or in front of Jupiter, never truly seeing what lay upon it. It wasn't until the 20th century that the picture began to change. In the early 1900s, a few careful observers noticed something curious. Io's brightness was not constant. When they aimed their telescopes at the moon, its light seemed to waver ever so slightly. It wasn't a dramatic flash, but a gentle, puzzling change, sometimes brighter, sometimes dimmer, without any clear reason. These changes didn't match Jupiter's eclipses or any known pattern. At first, most astronomers dismissed the flickering as a trick of the atmosphere or a flaw in their equipment. A sudden gust of wind, a thin cloud, or even the shimmering heat above the ground could cause a telescope's image to blur or jump. Light from Jupiter itself often spilled over and interfered with Io's glow, making it hard to know what was real. For decades, the strange variations were brushed aside. But as technology improved, the mystery refused to fade. Better telescopes, clearer lenses, and steadier mounts revealed that the changes were real. They were coming from Io itself. What had once been dismissed as an illusion slowly turned into the first hints that this small, distant moon was far more dynamic and alive than anyone had ever imagined. During the 1950s and 1960s, astronomers began to use new and more sensitive instruments called photoelectric sensors. These devices could measure light far more precisely than the human eye ever could. When scientists turned these sensors toward Io, one of Jupiter's moons, they discovered something truly curious. The readings showed that Io's brightness was not perfectly steady. Instead of producing a smooth and even light curve, there were small dips and rises, tiny irregularities that repeated in the same parts of Io's orbit around Jupiter. This was the first real clue that Io's surface might not be uniform. Some astronomers started to wonder if the moon's appearance changed slightly as it moved, perhaps because certain areas were brighter or darker than others. Maybe there were shiny patches made of ice, or reflective minerals that glimmered when sunlight struck them from the right angle. Or perhaps there were darker regions that absorbed more light, creating those strange little dips in brightness. The problem was that no one had ever seen Io's surface up close. Even when viewed through the most advanced telescopes available at the time, the moon appeared only as a tiny blurry disk, barely a few points of light across. Then something even more puzzling happened. In a few high-contrast photographs taken from observatories in Chile and Hawaii, astronomers noticed what looked like a faint blur surrounding Io. It wasn't visible all the time, and when it appeared it only lasted briefly. On certain occasions, when Io passed in front of Jupiter or crossed the path of a distant star, a thin haze seemed to hang near its edge. The effect was so faint that many researchers dismissed it as a trick of the telescope, a small distortion caused by the optics, or perhaps random noise from the photographic film. Still, a few scientists wondered if there could be another explanation. What if Io wasn't just reflecting sunlight from its solid surface? What if something around the moon, perhaps a thin layer of gas or fine particles, was scattering that light, creating a barely visible glow? Could it be that Io had a faint atmosphere, one so thin it could only be seen under very special conditions? Most astronomers did not take that idea seriously. At the time, Io was thought to resemble our own moon, cold, airless, and geologically dead. The suggestion that it might have an atmosphere, especially one that changed with time, sounded almost impossible. Yet, those flickers and faint hazes kept showing up, quiet reminders that something about Io wasn't as simple as it seemed. In the early 1970s, just before spacecraft were sent to explore the outer planets, a new generation of infrared detectors became available. Infrared light, unlike visible light, can pass through dust and gas more easily, and it also reveals heat. When astronomers used these detectors to observe Jupiter's moons, Io once again stood out. To everyone's surprise, the instruments detected warm spots on its surface. These were small but noticeable patches that emitted more heat than the surrounding areas. This finding did not match the common view of Io as a frozen and inactive world. If heat was escaping from its surface, that meant something inside the moon was generating energy. Perhaps there were underground processes, maybe even volcanic activity, though that seemed far-fetched at the time. The detected warmth was weak, and the instruments were not powerful enough to provide a clear explanation. Part of the reason these strange signs were so often ignored was that planetary science during that period did not expect small worlds to be active. Earth's moon, Mercury and Mars all appeared to be quiet and geologically dead. Their volcanoes had long ago stopped erupting, their surfaces frozen in time. By comparison, Io was even smaller than Earth's moon, so it was assumed to have lost whatever internal heat it once had. According to the theories of the day, there was no reason for Io to be geologically alive, so whenever something unusual was observed, whether it was a flicker of light, a faint blur, or a bit of unexplained heat, scientists tended to blame their instruments instead of questioning their models. But a few astronomers were willing to think differently. They began to consider whether the powerful pull of Jupiter's gravity might be influencing its moons in more active ways. One daring idea was that Jupiter's immense gravity could be stretching and squeezing its moons as they orbited, generating heat through friction deep within their interiors. If that were true, Io's inside might be constantly kneaded and twisted like soft clay, staying warm even after billions of years. This tidal heating, as it would later be called, could explain the mysterious warmth observed in the infrared images. It might also explain the flickering light, if volcanic plumes or gases occasionally rose from the surface, scattering sunlight before fading away. It was an imaginative theory, but still just that, a theory. Without close-up photographs, there was no way to confirm it. As the 1970s continued, more and more odd signals began to appear. Radio telescopes detected bursts of energy coming from near Jupiter. These were short, high-frequency pulses that seemed to align with Io's position in its orbit. It was as if something about Io was interacting strongly with Jupiter's vast magnetic field. Once again, Io seemed to be at the center of the mystery. It was glowing faintly in infrared light, producing radio bursts and showing irregular patterns of brightness. Clearly something active was happening there. But what exactly, no one could yet say. Even the best photographs taken from Earth remained disappointing. Io still appeared as a fuzzy ball with no distinct features. A few astronomers thought they could make out vague surface details. A darker patch here, perhaps a crater there, but the images were too poor to be certain of anything. Then, in the year 1979, everything changed. The Voyager 1 spacecraft launched by NASA reached the Jupiter system. Its cameras were far more advanced than anything available on Earth. As Voyager 1 flew past Io, it sent back the first detailed images of the moon's surface, and what those images revealed stunned the world. Io was not the cold, silent world everyone had imagined. Its surface was a dazzling mosaic of colours, yellows, reds and whites, caused by various sulfur compounds. Towering mountains and ridges stretched across its landscape, and in one extraordinary photograph there it was, a massive plume of material shooting more than 300 kilometres into space. It was a volcanic eruption, the first active volcano ever observed beyond Earth. That single discovery rewrote everything scientists thought they knew about small worlds. Suddenly, all the earlier mysteries made sense. The flickers of light were the distant signatures of eruptions. The faint haze around the moon was not a flaw in the telescope but gas and dust thrown high above the surface. The weak warmth detected in infrared scans was the glow of active volcanoes and molten rock. The strange radio bursts were caused by charged particles from Io's eruptions interacting with Jupiter's immense magnetic field. For decades, astronomers had looked at Io and seen only a lifeless rock, assuming it behaved like the moon we see each night from Earth. They had watched the moon's light curve, recorded its flickers, and photographed its faint glow, yet most had dismissed these as simple errors. But those subtle signs had been telling the truth all along. Beneath the cold appearance, Io was alive with violent activity. Voyager's flyby turned that faint suspicion into undeniable proof. It revealed a world constantly reshaped by volcanic explosions, rivers of molten sulfur, and shifting plains of newly deposited material. The bright and dark patches seen earlier from Earth were not random reflections. They were the changing faces of an erupting world. In the end, the story of Io is a lesson in curiosity and patience. Long before the spacecraft arrived, the evidence had already been there. The tiny dips in brightness, the faint glows, the puzzling heat, and the strange bursts of radio energy. But those clues were ignored because they did not fit what people believed about small moons. Only when Voyager 1 flew past and captured those unforgettable images did the truth finally come into focus. Far out in the deep darkness surrounding Jupiter, an extraordinary cosmic performance is taking place. 3 of its largest moons, Io, Europa and Ganymede, are forever locked in a repeating perfect rhythm. At first glance, their motion might seem simple, like tiny worlds circling their massive planet in silence. But the more closely you look, the more incredible the story becomes. Io, the innermost of the 3, takes a little less than 2 days, about 1 3/4 days, to complete one full orbit around Jupiter. Europa, which lies just a bit farther out, takes almost exactly twice as long, about 3.5 days. And Ganymede, the most distant and the largest moon in the entire solar system, takes a little more than 7 days to make a single trip around Jupiter, which is almost exactly 4 times as long as Io's journey. That precise timing is not a coincidence. It is a pattern, a mathematical harmony, a cosmic lock known as a 1-2-4 resonance. For every orbit that Ganymede completes, Europa circles Jupiter twice, and Io rushes around 4 times. Each of these moons tugs on the others with its own gravitational pull, creating an invisible network of forces that keeps them forever connected. They are not just mindlessly following Jupiter's immense gravity. Instead, they are constantly adjusting to each other's pull, as if keeping time in a grand celestial dance. The gravitational tugs are tiny, almost unnoticeable in a single moment, but over countless years they add up. It is like an unending conversation among the 3 moons, a soft, rhythmic exchange that keeps them locked together in perfect order. Imagine 3 dancers moving in circles around a grand ballroom floor. Each dancer follows a different path and speed, yet somehow, after a certain number of steps, all 3 return to the same position and begin again. Even if one dancer moves slightly too fast or too slow, the others subtly adjust their pace to restore the rhythm. That is what happens in the Jovian system. If one moon drifts slightly out of sync, the combined gravitational pull of the other 2 gently pulls it back into place. This pattern is not fragile, it is astonishingly stable. Astronomers believe it may have remained unbroken for billions of years, surviving even as Jupiter itself and its moons evolved. The gravitational resonance not only keeps their orbits steady, but also changes their shapes, especially that of Io. If Io existed alone, orbiting Jupiter without Europa and Ganymede, it would eventually settle into a perfect circle. Over long stretches of time, Jupiter's own tidal forces, its steady gravitational pull, would smooth out Io's path until it became completely round. But the resonance prevents that. Each time Io passes near Europa, it receives a tiny gravitational nudge, and every second time Europa meets Ganymede, their combined pull gives Io another small push. These regular repeated nudges keep Io's orbit slightly stretched, an oval rather than a circle. That small stretch might seem unimportant, but it is the secret to something far more dramatic. As Io moves around Jupiter in its slightly oval path, it speeds up when it gets closer to the giant planet and slows down when it moves farther away. The strength of Jupiter's gravity changes during each orbit, squeezing and stretching Io's interior like a soft rubber ball being pressed over and over again. This constant flexing creates friction deep inside Io, and that friction turns into heat, immense amounts of it. So much heat, in fact, that it powers the most violent volcanic activity anywhere in the solar system. Rivers of molten lava flow across Io's surface, enormous mountains rise from constant eruptions, and huge plumes of sulfur and ash burst hundreds of kilometers into space. Without this gravitational dance, Io would be just another cold, rocky world orbiting in silence. But because it is trapped in this intricate rhythm with Europa and Ganymede, its orbit never stops changing just enough to keep its interior alive and blazing with heat. And this dance affects the other moons too. Deep beneath Europa's smooth, icy crust, an enormous ocean of liquid water likely exists. The same tidal heating that twists and warms Io's rocky body also keeps Europa's ocean from freezing solid. Ganymede, the largest of the trio, experiences a gentler version of the same effect. It is covered in ice, has its own magnetic field, and bears traces of ancient tectonic movement, evidence that it too was once shaped by the pull of its neighbours. Every time Io completes an orbit, it lines up with Europa in a slightly different position, and the same thing happens between Europa and Ganymede. These repeating alignments form a continuous cycle that lasts a little over 7 days, like a cosmic heartbeat that never stops. Each alignment strengthens the gravitational balance, keeping the pattern alive rather than breaking it. In most planetary systems, small gravitational tugs between moons or planets can cause chaos over time. Their orbits can drift, overlap, or even lead to collisions. But the 1-2-4 resonance between Io, Europa, and Ganymede acts as a natural safeguard, pulling the moons back into order whenever they begin to wander. It is a self-correcting rhythm, elegant and ancient, that resists change with astonishing precision. This stable pattern has allowed each moon to develop its own unique identity. Ganymede, farthest from Jupiter, is a vast icy world with a calm surface and traces of long-vanished movement below. Europa, resting in the middle, hides a deep ocean beneath its frozen crust, a possible home for life, warmed by the same forces that power Io's volcanoes, and Io, closest to Jupiter, bears the most dramatic effects of all. A tortured, fiery surface constantly reshaped by its own inner heat. Farther away from Jupiter lies Ganymede, the largest of all moons in the solar system. Though it does not experience as much tidal heating as Io, it still feels the slow, steady pull of the great gravitational rhythm shared among Jupiter's 3 inner moons. This rhythm, called a resonance, acts like a cosmic heartbeat, connecting them through invisible forces of gravity. Scientists believe that this strange and beautiful pattern did not appear suddenly. Instead, it likely took shape gradually over countless ages, as the moons formed and slowly moved outward under the influence of Jupiter's immense tides. Over time, their orbits began to fall into step. One connection led to another, until a magnificent balance was born. First, Io and Europa became locked together in what is known as a 2-to-1 resonance, meaning Io completed 2 orbits around Jupiter for every single orbit of Europa. Later, Europa was drawn into a similar 2-to-1 resonance with Ganymede. The result was a grand pattern, a 1-to-2-to-4 relationship where Io circles Jupiter 4 times for every 2 times Europa does, and for every single orbit of Ganymede. Once this gravitational chain was in place, it became almost impossible to undo. The same forces of gravity that created the resonance also hold it firmly in place, keeping the system beautifully balanced. This rhythm doesn't just link the moons, it protects them. Without it, they might slowly drift apart, wander into new orbits, or even collide over the course of millions of years. Instead, the resonance keeps everything in harmony. like a cosmic dance that prevents chaos from taking over. Such patterns are not unique to Jupiter's realm. Similar resonances appear elsewhere in the solar system. Pluto and Neptune, for example, are locked in a 3-to-2 resonance, where Pluto completes 2 orbits for every 3 of Neptune's. Some of Saturn's moons also follow delicate resonant rhythms, but none are as striking or as powerful as the one shared by Io, Europa and Ganymede. Here, the resonance is not just a mathematical curiosity. Its effects are raw, visible, and extreme. On Io, the endless gravitational tug-of-war stretches and squeezes the moon's surface, turning solid rock into molten fire. Volcanoes roar across its plains, constantly reshaping the landscape. It is as if the harmony of the orbits above has carved a world of flames from the frozen silence of space, a reminder that even in the cold outer reaches of the solar system, gravity can create both beauty and fury. Out in the vast realm of Jupiter's mighty system, gravity is not the only power shaping the small, fiery moon called Io. Something else, unseen but just as powerful, surrounds and influences it, a giant magnetic force that stretches far beyond the planet itself. Around Jupiter extends one of the most enormous magnetic fields in the entire solar system. It spreads for millions of kilometers in every direction, dwarfing even the great planet it comes from. And there, caught within this invisible web, Io moves not only under the pull of gravity, but also under the grip of magnetism. This immense magnetic field, called the magnetosphere, is born from Jupiter's rapid spin and its strange metallic heart. Deep inside Jupiter, the tremendous pressure turns hydrogen into a metallic form that conducts electricity. Combined with the planet's fast rotation, it creates a natural dynamo, a huge magnetic engine. Jupiter spins once every 10 hours, an astonishingly quick pace for such a giant world. That spin drives powerful electric currents inside the planet, which in turn produce a magnetic field so vast it can stretch as far as Saturn's orbit when pushed outward by the solar wind. Within this magnetic bubble, countless charged particles, mostly electrons and ions, are trapped and flung around the planet at tremendous speeds. They form a vast ring of hot plasma that whirls around Jupiter like a glowing disk of energy. Io, orbiting right through this fiery belt, is constantly struck by the invisible storm. It doesn't move through empty space. It sails through a sea of electric and magnetic forces. These particles slam into Io like a fierce wind, not made of air, but of charged atoms. As Io travels through this magnetic ocean, it feels a kind of electric resistance, almost as if it were a metal sphere being pushed through a strong magnetic field. The motion creates electric currents and opposing forces. Io's thin atmosphere, made mostly of sulfur dioxide, becomes partially charged by sunlight and by the storm of particles from Jupiter's magnetosphere. Because of this, electricity can flow through it. In this process, Io behaves like a moving wire inside a gigantic generator. As it crosses the magnetic field lines, a voltage builds up across its surface. That voltage drives an electrical current through Io's atmosphere and out into the surrounding space. The result is a spectacular phenomenon known as the Io flux tube, an invisible glowing cord of electric energy that connects Io directly to Jupiter. Along this electric highway, charged particles stream along the magnetic lines between the Moon and the planet. When they reach Jupiter's upper atmosphere near its poles, they create glowing spots, auroras, not powered by sunlight, but by Io itself. Spacecraft such as Galileo and Juno have seen these brilliant lights dancing near Jupiter's poles, glowing proof of the electric bond between the two worlds. But this flow of current doesn't just make Jupiter shine, it also pushes back on Io. The electric currents flowing through Io's atmosphere create magnetic fields of their own, which interact with Jupiter's massive magnetism. This constant tug creates a kind of magnetic brake, a gentle but steady force that slightly resists Io's movement. Over immense stretches of time, millions of years, this braking effect can subtly change Io's orbit or slow its rotation ever so slightly. This is a quiet cosmic struggle, gravity pulling one way, magnetism pulling another. Most of the time, gravity wins, keeping Io locked in its familiar orbit. But magnetism never stops pushing, always whispering its invisible influence. What makes it even stranger is that Io itself may act like a giant electric battery. As it moves through Jupiter's magnetic field, parts of its surface can build up electrical charges. These charges don't stay still, they shift, grow, and sometimes suddenly release in bursts. Lightning might flash silently across Io's upper atmosphere, invisible to human eyes but detected by spacecraft instruments. Each discharge sends pulses of heat through the thin air, sometimes altering how particles escape into space. Behind Io, the movement through Jupiter's magnetosphere leaves a long, swirling trail, a turbulent electromagnetic wake, where particles are twisted and stirred. Though this wake doesn't directly change Io's path, it reveals how deeply the Moon is tied to its magnetic surroundings. The intense radiation from Jupiter's magnetic field also affects Io's atmosphere and surface. It can strip atoms away, especially when the Sun becomes more active. Sulfur and oxygen atoms released by Io's volcanoes can be ionized and caught by Jupiter's magnetic lines. These particles then spiral around the planet, forming vast donut-shaped plasma rings that encircle Jupiter. These plasma rings contain thousands of tons of material, much of it originally from Io itself. Through this process, Io constantly feeds Jupiter's magnetosphere. In return, the magnetosphere shapes Io's surface, its motion, and even its volcanic behavior. The two are locked in a powerful feedback loop. Io gives to Jupiter, and Jupiter reshapes Io. Even Io's daily movement feels the pull of this interaction. As it orbits, it moves through a magnetic field that rotates once every 10 hours, while Io itself completes an orbit in about 1 3/4 days. This mismatch creates friction and twisting forces, a torque, that drives electric currents across the Moon's surface. The twisting is gentle but unending, a constant magnetic grip that may slowly influence how Io spins over long ages. Bound by invisible chains, Io and Jupiter's magnetic embrace. Far out in the kingdom of Jupiter, where gravity rules like a mighty king, one of its moons, Io, lives under two masters. The first is Jupiter's tremendous gravitational pull, and the second is something unseen but equally powerful, the planet's immense magnetic field. Today, Io is tidally locked, meaning it always shows the same face to Jupiter, much like how Earth's moon always shows the same side to us. But it was not always this way. Billions of years ago, when Io first formed, it was a far more restless world. Back then, it spun freely in space, turning on its axis without care, while Jupiter's pull tugged at it again and again. But over time, those constant tugs became too strong to resist. The gravitational force stretched Io slightly, pulling harder on one side than the other, creating friction deep inside the Moon. That friction slowly stole away Io's freedom to spin. Eventually, gravity forced it into obedience, locking one hemisphere to always face Jupiter, forever bound in a celestial stare. Yet, even in this locked state, Io has not found peace. Though it no longer turns freely, the planet's invisible magnetic field still presses against it, tugging, twisting, and nudging ever so slightly. It is as if Jupiter's unseen hand is always testing Io's balance, never letting it truly rest. The Moon is constantly adjusting, shifting ever so slightly as these invisible pressures flow across its surface and through its interior. For scientists who study Io's orbit, this means the story is far more complicated than simple gravitational motion. When astronomers trace Io's path around Jupiter, they must account for more than just the mathematics of orbits and gravity. They must include the subtle, whispering effects of magnetism and electricity that dance unseen between the two worlds. The gravitational resonance that links Io to its neighbouring moons, Europa and Ganymede, creates a steady rhythm that keeps Io's orbit predictable. But the electromagnetic effects act like tiny corrections, almost like fine-tuning a musical instrument. These small changes are not easy to see. They appear in delicate, nearly invisible ways, in the tiniest shifts in Io's orbital timing, in faint patterns of light that ripple across Jupiter's auroras, and in the mysterious behaviour of the plasma torus, a glowing ring of charged gas that circles Jupiter along Io's orbit. To catch these faint signs, scientists use every tool they can. Spacecraft like Juno, orbiting Jupiter since the year 2016, carry instruments that can feel the planet's magnetic field and measure how it changes as Io passes through it. From Earth, telescopes use sensitive detectors to follow Io's movement down to fractions of a second. They track its shadow as it crosses Jupiter's cloud tops, compare its position year after year, and search for patterns that might reveal whether Io's orbit is slowly shifting, wobbling, or changing shape. Each small variation matters. Over decades, even the tiniest drifts can build up into something noticeable. A quiet reminder that Jupiter's magnetic grip is always working behind the scenes. While gravity explains most of what astronomers see, there are always leftovers, odd, unexplained fluctuations that hint at something more. Those irregularities may be the marks of Jupiter's invisible chains, the electromagnetic forces that connect planet and moon in a complex web of energy. Far out in the realm of Jupiter, there exists a glowing ring unlike anything else in the solar system. It is called Io's plasma torus, a giant donut-shaped belt of charged gas made mostly of sulfur, oxygen, and sodium ions. But this ring didn't just appear out of nowhere. It was born from the fiery breath of Io itself, the most volcanically active moon in our cosmic neighbourhood. It all begins on Io's turbulent surface, where volcanoes rage with unimaginable force. Each eruption hurls clouds of gas and ash high into the sky, so high that some of the material escapes the moon's gravity altogether. What begins as solid rock deep beneath Io's crust becomes hot vapour, and then, as it soars into space, it transforms yet again under the harsh light of the sun and the invisible power of Jupiter's immense magnetic field. Once these gases leave Io's surface, they begin to change. Sunlight bombards them, and streams of high-energy particles racing through Jupiter's magnetosphere smash into them. Electrons strike the atoms with enough force to knock some of their electrons free. This process turns ordinary gas into something far stranger: plasma. Plasma is not like the air we breathe. It's a fourth state of matter, made up of charged particles, positively charged ions, and negatively charged free electrons. Because these particles carry electric charges, plasma can behave in amazing ways. It can conduct electricity, it can generate and carry currents, and most importantly, it can be trapped and shaped by magnetic fields. Near Jupiter, those magnetic fields are titanic. They stretch for millions of kilometers in every direction, dwarfing even the giant planet itself. And within this vast magnetic web, the plasma from Io gets caught and molded into a thick glowing ring that wraps around Jupiter's magnetic equator. This ring, the plasma torus, extends roughly from Io's orbit and far beyond it, forming a colossal halo hundreds of thousands of kilometers wide. Even though the plasma torus is thin and spread out, it holds an enormous amount of energy. It shines brightly in ultraviolet light, flickering and pulsing as electric currents race through it. The entire ring spins with Jupiter's magnetic field, which sweeps around the planet once every 10 hours. That means the plasma whirls around faster than Io itself, overtaking the little moon again and again. Each time it does, it brushes against Io's thin atmosphere, stripping away even more material and feeding it back into the ring. This creates a powerful feedback loop. Volcanoes on Io release gas. Gas escapes into space. Sunlight and radiation turn it into plasma. The plasma joins the torus. The torus circles back, interacting with Io again, pulling more gas out. Round and round it goes, a cosmic engine fueled by volcanic fire and magnetic might. The main building blocks of the torus are sulfur and oxygen, both born from Io's volcanic plumes of sulfur dioxide. When a volcano erupts on Io, it shoots towers of gas dozens of miles high. Some of that gas cools, freezes, and falls back as frost, painting Io's surface in bright yellow and white patches. But a portion escapes completely. Once free in space, the gas is torn apart by sunlight and radiation, leaving sulfur and oxygen atoms drifting through Jupiter's magnetic field. Soon, high-energy electrons slam into these atoms, stripping away electrons and turning them into ions, the glowing heart of the plasma torus. Sodium, though less abundant, plays its own special role. When it becomes ionized, it emits a striking yellow glow, so vivid that Earth-based telescopes were able to detect it even before spacecraft ever reached Jupiter. Astronomers noticed these sodium emissions shimmering around Jupiter, and from them, they traced the source back to Io. When Io erupts violently, scientists can sometimes see the plasma torus brighten or shift shape in response. Imagine that. A single eruption on a small moon, nearly 800 million kilometers away, powerful enough to reshape a vast magnetic ring that circles a gas giant. No other moon in the solar system influences its planet's magnetic environment so dramatically. All that material blasted from Io becomes part of Jupiter's mighty magnetic system. The planet doesn't simply let it drift away, it captures it, wraps it in invisible magnetic lines, and spins it into a luminous ring of power. Within the torus, conditions vary depending on how close you are to Jupiter. Nearer to the planet, the plasma grows hotter and denser, energized by Jupiter's fast rotation and fierce radiation. Farther out, it becomes thinner and cooler, but the whole structure is alive. It breathes in a way, expanding and contracting, brightening and dimming as energy surges through it. Scientists have been studying this mysterious ring for decades. Spacecraft passing through Jupiter's system, as well as powerful telescopes back on Earth, have helped us map and measure it. Ultraviolet telescopes can see the torus glowing in invisible light, while spectrographs, special instruments that break light into its component colours, allow scientists to identify the fingerprints of sulfur and oxygen ions. By studying the wavelengths and brightness of that light, researchers can tell how fast the plasma is moving, how hot it is, and even how it changes over time. But the torus is not just a passive ring, it's dynamic and turbulent, stirred constantly by a process called plasma interchange instability. Think of it like a cosmic version of boiling soup. The hotter, denser plasma near Jupiter wants to rise outward, while the cooler, lighter plasma farther away wants to sink inward. This swapping motion keeps the whole system churning and alive, constantly mixing and redistributing energy and particles. It's this restless motion that helps the torus maintain its power and balance over time. The story doesn't end there. The energy stored in Io's plasma torus doesn't stay locked within the ring. Some of it travels along Jupiter's magnetic field lines down toward the planet's poles, where it crashes into the upper atmosphere. The result is breathtaking, blazing auroras, far more intense than anything on Earth. These are not gentle green lights like our northern and southern auroras. Jupiter's are fierce and fast, glowing in ultraviolet and infrared light, flickering with raw power. They are so bright that even spacecraft millions of kilometers away can detect them. And woven into these auroras, scientists have found what they call Io's footprint, a glowing mark that traces where Jupiter's magnetic field connects directly to Io, as if the moon had stamped its presence onto the planet's own atmosphere. In this way, Io and Jupiter are forever linked, a volcanic moon and a magnetic giant, locked in a cycle of fire and electricity. Each eruption on Io feeds the plasma torus, and the torus in turn feeds energy back into Jupiter's magnetosphere. It's a breathtaking example of how even a small world can shape the environment of a planet thousands of times its size. Far above Jupiter's swirling clouds, something extraordinary is happening. Where the invisible magnetic link between Io and Jupiter touches the giant planet's upper atmosphere, bright glowing spots appear, like sparks where two enormous electrical wires meet. These flashes mark the places where electric currents from Io's plasma stream flow down into Jupiter's polar regions, lighting up the planet's auroras. But the story doesn't end there. The enormous ring of charged gas known as the Io plasma torus is not perfectly sealed. It leaks. Not all the plasma, those energetic sulfur, oxygen and sodium ions, stays trapped inside the glowing ring that circles Jupiter. Some of it slowly drifts outward, spreading into Jupiter's outer magnetic field. Some of it escapes completely, carried off by the powerful flow of particles from the sun, known as the solar wind. Over time, this steady escape forms a gigantic invisible tail trailing behind Jupiter, stretching for millions of kilometers into deep space. It's almost like a long glowing trail of cosmic breadcrumbs, tracing the path of Io's particles as they drift away into the darkness. When spacecraft have flown through this tail, their instruments have detected clear traces of sulfur and sodium, proof that Io's influence reaches far beyond its orbit. It is astonishing to realize that volcanic eruptions, which we usually think of as fiery events that happen only on the ground, can shape the space environment around an entire planet. On Io, a volcano erupting on the surface doesn't just spill lava. It helps generate electromagnetic storms and even changes Jupiter's radiation belts. It's a powerful bridge between worlds, showing how geology and space physics can intertwine in ways almost impossible to imagine. Yet this connection happens every single day. Scientists are still studying how this strange system works. They want to understand exactly how the ions are accelerated, how energy moves between Io, the plasma torus, and Jupiter, and how the torus itself responds when Io's volcanic activity changes. Every eruption on Io might slightly shift the balance of electric currents and plasma flows. Missions sent to the Jovian system in recent decades have solved some of these puzzles, but each answer brings new mysteries. Researchers hope that future probes will one day fly through the torus again, taking direct samples and measurements to uncover more about this breathtaking cosmic dance. Now let's travel back to Io's surface, a world unlike any other moon in the solar system. If you look at most moons, you'll see ancient scars everywhere, craters, dents, and gouges left by billions of years of impacts. With no wind or rain to erase them, these craters remain frozen in time. On some moons, a single crater can last longer than life has existed on Earth, more than 4 billion years. But Io is nothing like that. When spacecraft first sent back close-up pictures of Io, scientists were astonished. They expected to see a battered, crater-covered landscape. Instead, they found a smooth, colourful world, painted in brilliant shades of yellow, red, and white. Towering mountains rose from the surface, but there were almost no craters anywhere. For a moon as ancient as Io, this was a mystery. Surely it must have been struck by countless meteoroids over time, especially since Jupiter's powerful gravity attracts so many space rocks and comets. So where were all the craters? The answer turned out to be both simple and incredible. They had been erased. Io's volcanoes are so active that they constantly rebuild the surface. Old craters are buried under fresh layers of lava, blanketed in sulfur, or covered by the frost and debris from countless eruptions. On Io, the ground never stays the same for long. In geological terms, the surface is reborn again and again, so quickly that craters vanish almost as soon as they appear. On other icy moons like Europa, Ganymede or Callisto, things are quiet and slow. Their surfaces are made of ice that changes only over immense stretches of time, millions or even billions of years. A crater on Callisto, for instance, might be more than 4 billion years old and still look nearly untouched. But Io is a world of constant motion. Its volcanoes are enormous, violent, and unpredictable. Some eruptions spread lava over areas as large as the US state of Texas. Some blast plumes hundreds of kilometers high into the sky. A single eruption can completely reshape an entire region. Even between major events, smaller eruptions happen constantly. Lava seeps out of cracks, forming new flows, while vents spray sulfur dioxide gas that later freezes into colourful frost. Over time, these materials pile up and spread, layering the surface again and again. This endless resurfacing means that Io's face is always changing. Bright yellow regions show where cold sulfur frost has settled, while darker patches reveal fresh, still warm lava. The darker the area, the younger it likely is, evidence of a recent eruption. In some places, scientists can see thick stacks of lava flows built one atop another, marking sites of repeated volcanic activity. These layers can grow several kilometers deep, showing just how fast and intense Io's geological renewal truly is. Because of this, Io's surface is considered remarkably young. Researchers estimate that, on average, no part of Io's surface is more than about 1 million years old, and many regions are likely far younger. In cosmic terms, that's practically brand new. The Moon is constantly painting over its own past, erasing its history faster than scientists can study it. This makes Io both fascinating and frustrating. With no craters to examine, it's difficult for scientists to uncover its ancient secrets. Yet, in another way, Io is a living laboratory, a place where the power of a world's interior is visible on its surface every day. On many moons across the solar system, scientists can tell a lot just by looking at the number and shapes of craters on their surfaces. Each crater is like a fossilized scar, a frozen moment from long ago, telling stories about the moon's age, about what kinds of objects have struck it, and even about what the solar system was like when it was still young. But Io, Jupiter's fiery moon, is different. It is a world where the past has been erased again and again. The usual record of impacts and ancient events, the craters, is almost completely gone. Instead of craters, Io's surface is alive with volcanoes, glowing lava fields, and constantly shifting plains. Scientists cannot study its history the way they do with other worlds. Instead, they have to watch Io change in real time. By comparing pictures taken years apart, sometimes a decade or more, they can actually see the landscape transform. Entire regions reshape themselves. A volcanic pit that once was wide and deep might look smaller the next time, or it might vanish altogether, buried under a river of new lava. In other places, bright new patches suddenly appear, marking where molten rock has poured out across the plains. It is as if the moon itself is breathing, its skin constantly renewing, cracking and healing again. This constant renewal makes Io a truly living world, one that changes fast enough for us to watch. Unlike ancient frozen moons covered in craters, Io's surface is fresh and ever-moving. And that lack of craters affects more than just how it looks. It also changes how heat moves through it. On heavily cratered moons, the landscape is rough and pitted, filled with deep holes that trap cold air and shadows. Io's newer surface, in contrast, is smooth and broad. Its lava plains radiate heat more evenly into space. When viewed through infrared instruments, some of these lava fields still glow softly, showing that they remain warm long after the eruptions that formed them have stopped. What is most surprising is how warm Io really is. Instruments have recorded temperatures far higher than anyone expected, for a moon of its size and distance from the Sun. This warmth clearly does not come from sunlight. It comes from within. Deep beneath its crust, Io's heat is born from tidal forces, the invisible but powerful stretching caused by Jupiter's immense gravity. As Io orbits the giant planet, Jupiter's pull squeezes and flexes the little moon like a rubber ball. This endless kneading stirs up tremendous friction inside, creating enough heat to melt rock and feed its countless volcanoes. That heat rises upward, cracking the crust and sending rivers of lava across the surface. Each eruption wipes away a bit more of the past, replacing it with something new. Yet not everything on Io changes overnight. Some features, like the tall, jagged mountains, endure for longer. These mountains are not volcanoes, but are thought to have formed when parts of Io's crust were pushed together by tectonic forces, like wrinkles forming on a squeezed orange. Some of them reach heights greater than Mount Everest on Earth, towering many kilometers above the plains. But even these giants do not stay the same forever. Over time, glowing lava creeps up their sides, and falling volcanic plumes settle on their peaks, coating them with bright new layers of sulfur and ash. Eventually, even the tallest mountains begin to wear away and disappear beneath Io's endless volcanic rebirth. To scientists, Io's smooth, craterless surface is not a sign of calm. It is a sign of constant chaos. It shows a world that refuses to sit still, a world where every inch of land is eventually destroyed and rebuilt. Studying Io means watching creation and destruction happen side by side, again and again. Unlike the silent, cratered surfaces of other moons, Io's surface is alive, a living record not of the distant past but of the present moment, a world that never stops changing before our eyes. Far out in the vast reaches of Jupiter's domain lies Io, a world unlike any other in the solar system. Its surface is alive, restless, and ever-changing, a strange landscape where fire and ice exist side by side, and where every day brings new scars to its battered face. When spacecraft look down upon Io, they see brilliant white patches, glowing yellows, deep reds, and streaks of black. A chaotic masterpiece painted by volcanoes and frozen gases. It is a moon that never rests, constantly reshaping itself under the combined forces of gravity, heat, and chemistry. The bright areas that sparkle on Io's surface are not made of snow, even though they may appear that way from orbit. They are covered with a thin, fragile coating of frozen sulfur dioxide, a kind of frost that forms from volcanic gases. When Io's volcanoes erupt, they do not only release molten rock, they also spew out enormous clouds of gas and dust. As this gas spreads into the frigid atmosphere and drifts across the surface, it begins to cool rapidly. Eventually the gas freezes and settles as a delicate frost, covering the plains in a thin layer that glimmers in sunlight. From a distance, these frozen fields shine like freshly fallen snow, but they are made of something far more exotic, a kind of frozen gas, not water ice. The sunlight that hits these frosty plains bounces off them and gives them their dazzling colours. Some appear bright white, while others glow faintly yellow, depending on how thick the frost is and how the sunlight strikes it. It is a beautiful sight, but also a fragile one. The frost is so delicate that even a small rise in temperature can make it vanish in seconds, turning it back into gas. Temperatures on Io can drop to astonishing lows, far below the freezing point of any water-based ice. In fact, some of the plains coated in sulfur dioxide are among the coldest surfaces ever recorded in the entire solar system. When night falls on Io and the sunlight disappears, the land cools rapidly. Without the warmth of the sun, the frozen sulfur becomes as hard and brittle as glass. The plains grow stiff and silent, locked in icy stillness beneath the dim light of distant Jupiter. Yet this stillness is an illusion. Beneath the frozen surface, tremendous forces are always at work. Io's peace is fragile because it lives under constant threat from its own volcanoes. One powerful eruption, even one that occurs hundreds of kilometers away, can send waves of heat or showers of ash sweeping across these frozen fields. The delicate frost melts, new materials settle, and the surface is reshaped in moments. What once looked like a smooth, bright plain may, within hours, turn dark and scarred, marked by the fingerprints of volcanic fury. But Io's surface is not only made of cold frost and frozen gas. There are also vast regions that are dark and molten, where rivers and lakes of lava flow freely. These dark spots are the scars of intense volcanic activity, pits, cracks, and broad flows where molten rock bursts through the crust. The lava that emerges from Io's interior is incredibly hot, far hotter than anything seen on Earth. Some of it forms enormous lakes that stretch for tens of kilometers, glowing faintly through Io's thin atmosphere like embers in the dark. These lava lakes are restless and unpredictable. They are not frozen or solid, but in constant motion. Beneath the dark crust that covers them, molten rock bubbles, surges, and shifts in a continuous cycle. The surface crust may cool and harden for a while, but eventually it cracks open, allowing new lava to well up from below. When that happens, the lake's surface glows again, releasing heat and light in a spectacular show of planetary power. The colour of these lava lakes depends on how hot they are and how fresh the molten rock is. Some are dull grey or nearly black where the lava is cooled, while others gleam in deep shades of red and orange when they are newly exposed. Each eruption paints the surface in different tones, creating a patchwork of colours that tell the story of Io's fiery heart. Among all of Io's volcanoes, one stands out as the most famous, Loki Patera. This massive volcanic lake is shaped like a horseshoe and is larger than Earth's Lake Ontario. It is one of the most active volcanic features in the solar system. Scientists believe that the surface of Loki Patera behaves much like a frozen pond on Earth during the spring thaw. The crust that forms on top of the lava slowly thickens as it cools, but over time, this crust becomes too heavy to float. Eventually, it collapses in huge sections, sinking into the molten rock below. When this happens, the lake brightens dramatically, releasing a burst of heat and light that can be detected even from Earth with infrared telescopes. These brightening events occur regularly, giving astronomers a way to track Loki's strange rhythm, a rhythm of destruction and renewal that never truly stops. Loki Patera is not alone. Across Io's surface lie many other volcanic pits known as paterae. Each of these pits is a deep depression formed by countless eruptions over time. They are surrounded by steep cliffs and often hold pools of molten rock or twisted flows of cooling lava at their base. Some paterae are so large that they could swallow entire mountains on Earth, while others are smaller but just as active. Within their walls, heat and pressure build constantly, waiting for the next eruption to tear through. Between the icy frost plains and the burning lava fields lie regions of incredible contrast, transition zones where the two worlds meet. These areas are full of complex patterns and vivid colours, created by the interaction of fire and frost. Here, a plume from a nearby volcano might shoot ash high into the sky, only for it to fall back down as a blanket of red, orange, or even greenish dust. Depending on the chemical makeup of the ash, especially its sulfur content, it can stain the land in brilliant hues. These colourful streaks and patterns can stretch for hundreds of kilometres, showing how far volcanic material can travel. Scientists study these markings closely, as they reveal valuable clues about the direction of Io's winds, the power of eruptions, and how quickly heat spreads across the moon's surface. In some places, you could walk only a few kilometres and move from an icy plain cold enough to freeze gas solid to a fiery region hot enough to melt rock. Such extreme temperature differences create immense tension on Io's surface. When molten lava spreads into an area covered in frozen sulfur, violent reactions occur. The heat from the lava instantly turns the sulfur frost into gas, which expands rapidly and sometimes explodes. These reactions can blast out small craters or cause shock waves that ripple across the surface. In this way, Io's surface is constantly reshaped not just by eruptions, but by the explosive meeting of its frozen and molten worlds. From space, Io does not look like any familiar moon or planet. It has no blue oceans, no green forests, and no smooth grey plains like our moon. Instead, it dazzles with a wild mix of colours: brilliant yellows, deep reds, shining whites, and patches of black. The entire surface looks like an artist's palette that has been smeared and splattered in every direction. This vivid variety is not just beautiful, it also helps scientists study how Io changes over time. By watching these colours shift, fade, or brighten, researchers can track volcanic activity from afar. When a lava lake expands or erupts, it leaves behind a dark patch that slowly cools. When frost settles over a cooled region, the area brightens again. These colour changes tell scientists where heat is rising from within, where gases are being released, and where new eruptions might soon appear. It is as if Io itself is sending out signals, marking the locations of its most active regions. Some volcanoes, like Patera, follow regular cycles that scientists can predict with some accuracy. They brighten, dim, and brighten again over a set period, like the steady rhythm of a heartbeat. Others, however, are unpredictable. They appear suddenly, erupting with little or no warning. These surprise eruptions can pour lava across vast areas, creating entire new lava fields in just a few days. When that happens, old features are buried, and the landscape is transformed completely. A region that once gleamed white with frozen gas can, within weeks, become a dark sea of cooling rock. Because of this endless cycle of destruction and renewal, there are very few places on Io that remain unchanged for long. The moon's surface is in constant motion, though we cannot see it moving in real time. Even the frozen sulfur plains, which might seem eternal and still, can vanish overnight if a new eruption occurs nearby. Meanwhile, lava lakes that were once roaring with heat can slowly cool and harden, forming dark, solid plains where faint warmth lingers below. Some of these cooled lakes may remain dormant for years, only to come alive again with fresh eruptions that tear through their crusts and restore their molten glow. Io is, in many ways, a living world, not alive in the sense of plants or animals, but alive with movement, transformation, and raw energy. Its surface is shaped not by weather or water, but by fire, frost, and the relentless forces within. Every eruption adds new layers to its story. Every plume of ash and every frozen field tells of a delicate balance between heat and cold, between creation and destruction. From a human point of view, Io might seem chaotic, even violent, a place where the ground never rests and where beauty and danger exist side by side. But to scientists, it is a treasure, a window into the forces that shaped not only Io, but also the early Earth and the other worlds of the solar system. Studying Io helps us understand how volcanic worlds work, how planets cool and heat over time, and how surfaces can change on a global scale. Io, one of Jupiter's most fascinating moons, has an atmosphere so thin that if you were somehow standing on its surface, you wouldn't even notice it. There would be no feeling of air pressing against your skin, no whisper of wind, and no blue sky spreading above you. Light from the sun would fall directly from the blackness of space, and no clouds would ever drift by to block it. You could walk across the ground for hours, and, without sensitive instruments, you might never even suspect that an atmosphere existed there at all. The main ingredient in this ghostly atmosphere is a gas called sulfur dioxide, or SO2. Here on Earth, sulfur dioxide is something we mostly think of as a pollutant, a choking gas you might smell near a volcano, or when coal or oil burns. But on Io, this gas is not rare or accidental. It is everywhere, filling the thin sky and coating the ground. Volcanoes constantly belch it out in enormous plumes that can rise many kilometers high. When the gas cools and settles, it freezes onto the surface as bright white frost. This frozen layer doesn't stay solid forever. When sunlight touches it, the frost warms up and begins to change, turning back into gas and drifting upward once again. For a few hours every day while Io faces the Sun, this process creates a delicate temporary atmosphere, a faint veil of gas surrounding the Moon. But this fragile atmosphere is short-lived. As soon as the Sun sinks below the horizon and night falls on Io, the surface temperature plunges. Without sunlight to warm it, the frozen world cools rapidly, and the gas that floated above the surface begins to vanish. The sulfur dioxide doesn't simply thin out, it freezes. The entire atmosphere collapses. This astonishing transformation happens every single night on Io. The sulfur dioxide that once floated freely in the sunlight condenses into tiny crystals that gently fall back to the ground, covering the night side of the Moon with a fresh layer of frost. Scientists have a name for this daily event. They call it atmospheric collapse. It is one of the few places in the solar system where we can watch such a thing happen so completely and so regularly. There is no real weather here in the normal sense, no winds, storms, or rain. Instead, Io experiences this slow and rhythmic breathing, gas rising during the day and freezing out at night, all controlled by the simple rhythm of sunlight and shadow. When Io spins back into daylight, the frost begins to warm again. There is no melting because Io is far too cold for any liquid to form. Instead, the frost skips the liquid stage entirely. It turns straight from solid to gas. This process, called sublimation, fills the air with sulfur dioxide once more, recreating the thin atmosphere that will last only until the next sunset. Even though this atmosphere is almost non-existent by earthly standards, its pressure is only about 1/billionth of what we feel at sea level on Earth. It still undergoes dramatic changes. During Io's daytime, the pressure can be up to 10 times higher than at night. On a planet with a thick atmosphere, such huge changes would stir up violent winds or storms. But on Io, where the air is so thin that molecules barely collide, it simply means the atmosphere appears and disappears every 42 hours, the length of one full day on Io. From orbit, spacecraft have actually observed this astonishing cycle. Instruments that study how sunlight passes through Io's atmosphere have recorded clear signs of sulfur dioxide gas when the Moon is bathed in light. But when Io moves into Jupiter's shadow, blocking the Sun's rays, that gas vanishes almost immediately. There is practically no delay. Io's atmosphere reacts to sunlight as if it were directly tied to it, fading the instant the light disappears and reviving the moment it returns. This makes Io's air behave more like steam than true air. On the day side, gas rises and spreads. On the night side, it freezes and falls. At the border between night and day, the region scientists call the terminator, this transformation happens with remarkable speed. You can almost imagine an invisible tide of gas sweeping around the Moon as it turns, forever chasing the Sun. Over time, this strange cycle shapes Io's surface in subtle but important ways. The coldest regions, which spend the longest time in shadow, tend to accumulate thick, sparkling layers of sulfur dioxide frost. In contrast, warmer regions, especially near active volcanoes, may never allow frost to settle at all. Between these extremes lies a patchwork landscape, zones where the faint atmosphere gathers and zones where it fades away, creating a constantly shifting mosaic across the Moon. Every volcanic eruption adds new complexity to this cycle. When a volcano bursts open, it can spew vast amounts of sulfur dioxide gas high into the sky. If this happens while that region is in daylight, the eruption can temporarily thicken Io's atmosphere, forming a larger plume or denser patch of gas. But if an eruption occurs during the long night, most of that gas freezes almost instantly, falling back as frost before it has any chance to spread. So even the timing of a volcanic eruption, whether it happens under sunlight or darkness, determines whether the gas becomes part of the atmosphere or part of the frost-covered surface. This endless repetition of freezing and thawing is not just a fascinating scientific curiosity, it may also be changing Io's face over time. Scientists believe that as frost builds up and later sublimates, it could carry away fine dust and sulfur particles, gently cleaning and reshaping the surface. Each day and night cycle might polish the Moon's plains, sweeping away tiny grains and leaving the surface gleaming bright. Over hundreds or even thousands of these cycles, this delicate process could explain why Io's landscapes look so clean, smooth, and vividly coloured when seen from space. In a way, Io's surface undergoes a kind of natural cleansing ritual, a slow, steady renewal powered entirely by the warmth of the sun and the chill of space. It is a world without winds, without rain, without seasons, but not without rhythm. Every 42 hours, Io inhales sunlight and exhales frost, endlessly repeating this fragile dance between fire and ice, between day and night, in the vast shadow of mighty Jupiter. On Earth, the air around us never disappears. It changes temperature, it moves, it becomes thicker or thinner, but it always stays. Even on Mars, where the atmosphere is much thinner, it remains in place, clinging to the planet even during its coldest nights. But on Io, one of Jupiter's restless moons, things are completely different. There, the atmosphere does not stay put. It lives and dies every single day. When the sun rises over Io's strange landscape, heat awakens a thin breath of gas. Frost on the surface begins to vaporize, and a fragile atmosphere forms. But when the sun sets, that faint air freezes again and falls back to the ground as frost. It is an atmosphere that doesn't last. It is born at sunrise and gone by sunset, like a brief breath of life tied to the turning of the world. This fragile cycle reminds us that not all worlds are steady or calm. Io is constantly changing inside and out. To understand why, scientists look deeper, not just at its surface but at its shape, because the shape of a world can tell a lot about what is happening deep inside it. Every large planet and moon in our solar system takes on a form that reflects the forces within it. Worlds that spin, like Earth, Jupiter, or Io, often become slightly flattened at the poles and bulge a little at the equator. The spinning motion creates an outward push, and over millions of years this makes the equator rise just a bit higher than the poles. Earth has this bulge, Jupiter has it too. Io, though much smaller, follows the same rule. But Io's shape isn't created by rotation alone. Gravity, heat, and the materials inside it also play their parts. Spacecraft flying past Io have measured its size and contours with great precision. These measurements reveal that Io is slightly squashed at the poles and puffed out around the middle, exactly what we would expect from a spinning moon. Yet, the fine details of that shape hide clues about what lies beneath its surface. The way Io bulges, or fails to bulge, tells scientists how flexible or rigid its interior might be. This depends on what it is made of and how it is layered. To study this, scientists measure something called the second-degree gravitational harmonic, a fancy term that describes how mass is spread out inside a body. If Io's mass is tightly packed near its center, its gravity behaves differently than if its mass is more evenly spread. By combining gravity readings from spacecraft with measurements of Io's visible shape, scientists can build models that reveal what its interior might be like. These models suggest that Io is not a simple ball of rock. Instead, it has layers, much like Earth does. At the very top is the crust, the surface we see, covered in rock, sulfur, and frozen sulfur dioxide. Beneath that lies a thick mantle where Jupiter's tidal pull twists and heats the material, creating enormous energy. And at the heart of Io may lie a dense core made mostly of iron or an iron-sulfur mix, which could be molten or partly molten. None of this has ever been seen directly. All of it has been carefully inferred from the way Io moves and how it responds to Jupiter's gravity. If Io's core were solid and completely rigid, the Moon would behave differently. It would wobble less and bulge in slightly different ways. But if the core is partly molten, Io would move more flexibly, with its surface rising and falling more dramatically as it orbits Jupiter. This motion, Io's subtle stretching and relaxing, is called tidal deformation. Jupiter's enormous gravity pulls on Io unevenly. As Io moves around its giant parent, it is squeezed and released over and over again. This constant kneading generates immense internal friction, turning motion into heat. That heat fuels Io's volcanoes, making it the most volcanically active world in the entire solar system. But the amount of heat Io produces depends on how its interior is built. If its core were solid and stiff, much of that tidal energy would simply vanish as vibrations. But if its mantle and core are soft or molten, they can absorb and store energy more efficiently. This keeps the interior hot and feeds Io's fiery surface. The exact shape of Io, how much it flattens, how much it bulges, and how it moves, helps scientists figure out which of their models fit best. Over time, the precise measurements rule out certain ideas and support others. One of the most surprising discoveries is how closely Io's surface matches its inner structure. Tiny hills, plateaus, or depressions on the crust often mirror changes deep inside the Moon. For example, some regions on Io sit slightly higher or lower than others. When scientists compare these elevations with gravity data, they find that the differences may come from variations in density below the surface. In some areas, the crust might be thicker. In others, the mantle may rise closer to the top. These variations can even show where magma may be more likely to break through and erupt. There is also evidence that Io's overall shape is slowly changing with time. Some parts of the surface might be gently rising or sinking. These movements are very small, measured in meters rather than kilometers, but they matter greatly to scientists. Even tiny shifts can influence how the Moon's interior is modelled. Io also interacts with its neighbouring moons, Europa and Ganymede. The gravitational pull among them slightly alters their orbits. Europa and Ganymede tug on Io, and Io tugs back. These mutual forces change how Io is stretched and squeezed, affecting its internal structure. If Io's core were fluid, it would respond more dramatically to these outside pulls, and this response shows up in precise tracking data. A world with a solid, uniform interior would spin evenly and steadily. But if different parts of the inside rotate at slightly different speeds, something that can happen if the core is partly molten, then the Moon's spin can shift subtly over time. These tiny irregularities, though almost invisible, give scientists clues about how Io behaves deep within. Each piece of data, its shape, its gravity field, its orbit, its rotation, and even its surface changes, tells a part of Io's story. Together, they reveal a world that is layered, heated, and alive with motion beneath its surface. And all of this knowledge has been gathered without ever drilling into the crust or landing on its surface. By watching how Io moves, how it reacts to Jupiter's power, and how it twists under cosmic forces, scientists have peeled back the layers of this fiery moon to glimpse its hidden heart. At the centre of this story lies the mantle in motion. Unlike the dense metallic core, the mantle is made mostly of silicate rock. On most rocky worlds, including Earth, the mantle is mostly solid, moving only slowly over long stretches of time. But on Io, things are different. The intense tidal squeezing from Jupiter constantly stirs and heats the mantle. The pressure and heat soften the rock, causing parts of it to melt, not completely, but enough to make it behave like thick syrup or soft taffy. Scientists describe Io's interior as magma-rich, a place where small pockets of molten rock are mixed in with solid material. These molten zones can move, flow, and shift under the Moon's surface, feeding the volcanoes that light up Io's night side. It is a world in motion, its air freezing and thawing, its crust stretching and bending, its heart burning with hidden fire. As the giant planet Jupiter pulls on its small fiery moon Io, the whole world trembles and stirs. Deep beneath the colourful surface, molten rock churns like a thick soup being stirred by invisible hands. The enormous gravitational pull from Jupiter bends and flexes Io's rocky body again and again, squeezing it slightly as it moves through its orbit. Every time Io bends, its insides heat up. This constant kneading doesn't happen smoothly or gently. It's wild and chaotic, like a blender with no lid, splattering energy and molten rock in every direction. Inside Io, the hot material from deep below is pushed upward, while cooler rock sinks down toward the interior. This endless motion keeps the heat from building up in one spot. Instead, it spreads through the whole mantle, the vast layer between Io's crust and core. That's why volcanoes can appear almost anywhere on Io's surface. Every part of the Moon's interior is alive, constantly shifting, warming, and reshaping itself. Scientists have built computer models to study how this hidden motion works. They enter numbers for how strong Jupiter's pull is, how thick Io's crust might be, and how hot the inside gets. Then they let the computer simulate the dance of heat and movement over time. What they've discovered is fascinating. Most of the heat doesn't come from the core or the surface, but from the middle, deep inside the silicate mantle. That's where tidal energy gets trapped and turned into heat. The same heat that powers Io's incredible volcanic eruptions. The more molten the mantle becomes, the easier it moves, and the more it moves, the hotter it gets. This creates a feedback loop, a cycle that keeps feeding itself. But there's a delicate balance. If Io's mantle becomes too hot and melts too much, it starts to behave like a liquid and loses its shape. When that happens, Io's response to Jupiter's gravity changes and the heating becomes less effective. Scientists believe Io sits right in the perfect zone, part solid, part molten, flexible enough to stretch but still able to resist total collapse. Just as Earth's mantle has places that are hotter or cooler, Io's interior likely has regions where the melting is more advanced. These molten zones may feed particular volcanoes, or cause some areas of the surface to shift and rise more than others. Some scientists even think that hot columns of molten rock called Mantle plumes rise slowly from the deep interior toward the crust. These plumes might explain why some of Io's biggest volcanoes, such as Pele and Loki Patera, remain active for years at a time. Unlike the icy mantles of outer moons or the deep gaseous interiors of giant planets, Io's mantle is almost entirely rocky. It is mostly made of silicate minerals such as olivine and pyroxene, materials that can soften under heat but don't melt completely. Because of this, Io's mantle doesn't turn into a full ocean of magma. Instead, it behaves more like a very thick paste that can slowly deform and move. This partial melting makes Io flexible. It doesn't act like a solid stone world, but more like a giant breathing creature, stretching and relaxing as it travels around Jupiter. By studying how much Io flexes under Jupiter's pull, scientists can learn about the softness of its interior, how deep the molten layer goes, and how quickly material flows inside. The Galileo spacecraft, which orbited Jupiter in the 1990s, captured images showing volcanoes erupting all over Io, at different longitudes and latitudes with no single place ever staying quiet for long. This constant and widespread volcanic activity supports the idea of a mantle in motion, a world whose heat is not fixed in one place, but constantly on the move, like boiling soup that bubbles everywhere at once. While other worlds, like Earth's moon or the planet Mars, have cooled and grown quiet over billions of years, Io remains restless. Its interior never had the chance to freeze solid. Jupiter's enormous gravity keeps pulling and twisting Io, turning orbital energy into friction, and friction into heat. That endless heating is what keeps Io alive with activity, feeding its glowing lava lakes, its fountains of sulfur, and its fiery rivers of molten rock that streak across the surface like veins of light. This inner churning also cracks Io's crust, revealing signs of what scientists call subsurface intrusions. These are hidden movements of magma beneath the surface. The great volcanoes of Io, such as Loki Patera and Pele, release huge amounts of energy, but the lava that bursts out doesn't always come directly from the core or the deepest parts of the mantle. Instead, it seems that Io has a shallow, tangled network of magma chambers and underground passages, something like a planetary plumbing system, that channels molten material toward the surface. We can't see this network directly, but its effects appear in the way volcanoes behave. Using infrared cameras during spacecraft flybys, scientists have watched how Io's temperatures change over time. When a region suddenly heats up, or when a lava lake grows larger, it hints that magma has pushed into a new space below the crust, a shallow chamber filling up with molten rock. Sometimes this magma doesn't make it to the surface. Instead, it pushes against the crust, causing it to bulge and crack slightly, much like dough swelling under heat. Then the magma cools and hardens underground, forming solid structures of rock. When the molten rock moves upward through the crust, it creates a vertical sheet called a dike. When it spreads sideways between layers, it forms a sill. On Earth, these same kinds of structures are found in ancient volcanic regions, silent records of past eruptions. On Io, the evidence from heat maps and repeated observations suggests that dikes are common. When magma forces its way upward, it fractures the brittle crust, opening pathways for future eruptions. These cracks can stay open for a long time, allowing magma to rise again and again. A single dike intrusion might last a few hours or several days, slowly pushing molten material toward a vent. But sometimes, the pressure builds too quickly. When the crust above can no longer contain it, the surface breaks apart in a sudden explosion, releasing lava that floods across hundreds of square kilometers. The strongest eruptions on Io probably begin in this way, with a deep surge of pressure from below that finally bursts through the surface. By observing the same locations during repeated flybys, scientists have seen patterns that support this idea. Eruptions often reappear in the same regions, showing that Io's crust is continually cracking, refilling and breaking again. Io, though only a small moon orbiting a distant planet, behaves like a world in constant creation. Its surface is young, reshaped again and again by its own fiery heart. There are no oceans, no air to breathe, and no plate tectonics as on Earth, yet it remains one of the most geologically active places in the entire solar system. Under Jupiter's watchful gravity, Io's interior continues to churn, melt, and rise, forever painting its surface with rivers of fire and frozen sulfur, a living world sculpted by motion, heat, and time itself. Imagine standing above Loki Patera, one of Io's most fascinating volcanic features. At first glance, it looks dark and quiet, as if the surface has cooled into a hard, lifeless crust. But then, every so often, something remarkable happens. A great wave of molten lava sweeps across the basin, glowing brightly in infrared light, as though the moon's heart has begun to pulse again. Scientists think this glowing wave begins deep below the surface, when the molten rock, or magma, suddenly overturns. The cooler, hardened layer on top sinks downward, and the hotter material from beneath bursts upward to take its place. Before this dramatic overturning begins, molten material is thought to gather in a hidden pocket, or reservoir, lying just below the surface. A narrow channel or a dike connects this pocket to the floor of the lava lake. When pressure inside the chamber builds high enough, the surface above it cracks open, allowing lava to surge upward. On other parts of Io, volcanoes behave differently. They erupt like fountains or send up tall plumes of molten rock and gas. These kinds of eruptions likely come from vertical dikes that push rapidly upward through the crust. The way an eruption unfolds depends on the shape and size of these underground channels and on how much gas is mixed with the magma. A narrow dike or one filled with gas can make an eruption more explosive, while a wider one allows lava to flow more steadily. Over time, the repeated movement of magma through these dikes can reshape Io's surface. Each intrusion pushes the crust around, sometimes causing it to swell, to crack, or even to collapse into large pits. Images taken by the Galileo spacecraft revealed strange patterns near many of Io's volcanoes: ridges, depressions, and warped planes that hint at the restless activity below. Many of these surface features line up with places that have erupted again and again, suggesting that the plumbing system beneath Io's crust is constantly remolding the landscape. The immense energy that drives all of these surface changes comes from deep inside Io, not from the moon's core, but from the powerful tidal heating in its mantle. As Io orbits Jupiter, the giant planet's gravity stretches and squeezes the moon again and again. This flexing motion generates heat inside the rock, which keeps it partially molten. The molten material then rises through cracks and pockets, sometimes collecting in hidden chambers, sometimes breaking through the crust to form glowing lakes or violent eruptions. Scientists believe that as this molten rock rises, it doesn't follow one simple path. Some of it moves upward through thin cracks that form dikes. Some spread sideways into underground reservoirs beneath volcanic calderas and lakes. Modelling these hidden structures is extremely difficult, since no one can look inside Io directly. Researchers must piece together clues from afar, studying thermal maps, measuring how often eruptions occur, and examining the colour and chemical makeup of lava deposits. Each clue helps them guess how the magma moves below the surface. Not all magma behaves the same way. Thick, sticky magma builds up more pressure before it breaks through, leading to more violent explosions. Thinner magma can slide easily through cracks and flow gently across the surface. In some places, Io's crust may be thin, making it easier for magma to reach the top. In other areas, layers of hardened rock may act as a barrier, forcing the molten material to search for new routes or gather strength before erupting. Because of these differences, Io's surface is a patchwork of activity. Some regions blaze with eruptions year after year, while others remain quiet for long stretches of time, waiting for the next opening to appear. This idea of a shallow plumbing system isn't unique to Io. Earth's volcanoes have similar systems buried beneath their surfaces. Before a volcano like Mount St. Helens erupted in the year 1980, magma slowly pushed into underground chambers, building pressure until it burst outward. On Mars, enormous dikes once sliced through the crust, feeding ancient lava plains that now lie silent. But Io's version of this system is far more active and extreme. Its crust is thin, its surface is constantly stretched and squeezed by Jupiter's gravity, and its entire face is renewed again and again by erupting lava. It is a world in motion, a place where molten rock is always finding new paths upward. For scientists, Io is like a natural laboratory, a world where volcanic processes can be studied in their rawest form. Unlike Earth, Io has no atmosphere, no water, and no forest to hide its activity. Every eruption is laid bare, glowing against the blackness of space. This makes Io one of the best places to study how magma moves, erupts, and reshapes a planetary body. What makes this even more astonishing is that Io's constant activity doesn't come from its own internal fuel. Most planets and moons in the solar system slowly cool over billions of years. Their internal heat, left over from formation or from radioactive decay, eventually fades away. Their volcanoes die, their surfaces freeze, and their landscapes grow still. But not Io. Io's power comes from outside, from the giant hand of Jupiter itself. Every time Io orbits its massive parent planet, Jupiter's gravity stretches it like taffy. This squeezing and relaxing creates friction deep inside Io, and that friction turns into heat. It's a never-ending energy source, as long as Io's orbit continues in perfect rhythm with its neighbouring moons Europa and Ganymede. Together, these three moons are locked in a stable gravitational dance called a resonance, which keeps Io's orbit slightly stretched and prevents it from ever settling into peace. Io has remained volcanically alive for billions of years. Its heat output is enormous, second only to Earth among all rocky worlds in the solar system, even though Io is far smaller. And unlike Earth, Io's heat doesn't come from leftover formation energy or radioactive decay. It's created continuously by tidal flexing. This system is so stable that scientists believe it can keep generating heat for billions of years more. Computer models that simulate Io's orbit and interior have shown that the tidal forces can maintain this energy flow indefinitely. As Io flexes, the heat travels upward through its rocky mantle, reaches the crust and escapes through volcanoes, but never fast enough to cool the moon down completely. Jupiter's pull constantly injects fresh energy, keeping the system balanced in a kind of fiery equilibrium, and Io may not be the only world powered this way. Far beyond our solar system, scientists have discovered exoplanets orbiting very close to massive worlds. Some of them might experience the same kind of tidal heating that keeps Io alive, turning them too into worlds of constant fire, glowing under the pull of their giant neighbours. Among all the worlds in our solar system, Io remains the most striking and dramatic example of how powerful gravitational forces can shape a celestial body. Its entire surface is a record of endless struggle and renewal, marked by cracks, flows, and eruptions caused by the immense friction within. The crust of Io never truly rests. It is constantly being torn apart, melted, and rebuilt. Beneath its colourful plains, hidden forces are always at work, pushing and pulling, feeding the restless motion that defines this extraordinary moon. In many places, Io's crust is unusually thin, stretching over deep chambers filled with molten rock. As magma swells and shifts inside these chambers, the ground above bends and breaks, releasing bursts of energy in the form of spectacular volcanic eruptions. This constant reshaping is the result of Jupiter's powerful gravitational pull, which squeezes and stretches Io every time it orbits. The process never stops, and because of this relentless stress, Io's interior never gets a chance to cool and harden. Most moons eventually develop thick, stable shells that trap their inner heat and slow down geological change, but not Io. The heat inside is too intense and too steady for any permanent crust to form. The surface remains fragile, porous, and unstable, always reshaped from below like a living, breathing landscape of fire and frost. Io's orbit does more than guide its path around Jupiter. It defines its very nature. Few places in the solar system show such a close connection between movement and geology. Understanding how Io manages to stay so active helps scientists learn how other worlds might generate and maintain energy without the usual sources like sunlight or radioactivity. It also gives a glimpse into what might be happening on distant exoplanets and moons, where gravity and motion intertwine in equally complex ways. To truly understand Io, scientists must uncover how heat moves through its body, how energy born deep inside rises, spreads, and escapes. On Earth, Heat travels slowly upward through the mantle in large convection cells, building pressure until it bursts through volcanoes and cracks. Io behaves differently. To study it, researchers use special tools like thermal imaging and geophysical mapping, which let them see the moon's invisible heat patterns. Using data collected by the Galileo spacecraft in the 1990s, and later by infrared telescopes on Earth and spacecraft such as Juno, scientists have pieced together a detailed picture. Io's surface glows with hundreds of tiny hotspots scattered like embers across its surface. Many are active volcanoes, but others are simply warm regions with no visible eruptions. Some glow steadily for years, while others flare brightly before fading again. The most important tool in this exploration has been infrared sensing, which detects the heat radiating from the surface. Volcanoes such as Loki, Pele and Tvastar shine like beacons on these thermal maps, sometimes glowing brighter than the rest of the moon combined. But the heat is not always concentrated where eruptions occur. Often, it forms long curving bands that stretch for hundreds of kilometers, suggesting that heat can flow sideways through the crust before finally escaping into space. One of the key instruments in this research was the near-infrared mapping spectrometer, known as NIMS, aboard Galileo. This instrument revealed how temperatures on Io change over time. Some volcanoes maintain a steady output for months or even years, showing that they are connected to deep, stable reservoirs of magma. Others display pulsing patterns, where the surface heats and cools in cycles, hinting at molten rock moving through underground pipes and chambers, pooling and then breaking through. Perhaps most intriguing is how much heat Io gives off even when no eruptions are visible. There are vast regions where warmth seeps out quietly through the crust, unnoticed except in infrared light. These areas may represent slow lava flows moving beneath a crust of solidified rock, or intrusions of magma that rise close to the surface but never quite emerge. This silent heat tells scientists that Io's energy is not just released in dramatic explosions, it also leaks away gradually, through gentle warming and long-lived hotspots that can persist for years. By combining data from different instruments and missions, researchers have created what they call a thermal blueprint of Io. This map reveals that most of the moon's heat escapes near the equator, while the poles are cooler but not entirely inactive. This uneven pattern may mean that Jupiter's gravitational flexing is strongest around the equator, or that the crust there is thinner, allowing heat to rise more easily. Some models even suggest that a partially molten layer lies just beneath the crust, acting like a sponge for heat. This layer could collect energy from deeper down and send it through cracks and networks of molten rock before releasing it at the surface. Heat on Io does not always travel straight upward. It can move sideways first, spreading across large areas before breaking through at weaker spots. This explains why the infrared images show long glowing arcs instead of isolated hot dots. Another clue comes from the way Io's volcanoes behave over time. Some, like Loki, follow a predictable rhythm. The surface of Loki's lava lake seems to overturn in cycles, as if a vast sheet of molten rock periodically sinks and is replaced by fresh lava from below. The timing of these events matches changes in Io's orbit around Jupiter, showing that the moon's interior reacts quickly to shifts in gravitational pressure. This means that Io's heat isn't only stored in deep, slow-moving chambers, it also travels through fast, shallow systems that respond almost immediately to external forces. Observations in the mid-infrared range have revealed even more mysteries, hidden heat sources that don't appear in visible light and have no clear volcanic vents. These could be pockets of magma trapped beneath the crust, or areas where lava flows silently under solid rock, never quite reaching the open air. Such discoveries have taught scientists that Io's heat budget, the balance between energy produced and lost, is far more complicated than anyone once imagined. To study this delicate balance, scientists also use Earth-based telescopes to observe Io during its eclipses, when Jupiter's shadow blocks sunlight. In these moments of darkness, every natural glow from Io stands out clearly, allowing researchers to watch the heat of its volcanoes and hotspots as they brighten and fade. Each observation brings us closer to understanding this fiery world. A moon that never sleeps, whose heartbeat is measured not in days or seasons, but in the eternal rhythm of gravity, heat and motion. When the giant planet Jupiter casts its vast shadow over Io, the temperature on the moon's surface drops almost instantly. The once glowing plains turn cold and dark in moments, Yet, even in that deep shadow, certain places on Io continue to shine faintly. Its volcanoes and hot spots. They keep their warmth, glowing with the hidden fire that never truly fades. By carefully observing how the warmth from these areas weakens over time, scientists can tell how deep the heat comes from within the moon. If the heat disappears quickly, it suggests the lava layer on top is thin. If it fades slowly, it means the heat is buried deeper or insulated by thicker material. From this, researchers have learned to read Io like a living map of fire. By combining many years of observations, they have created global heat flow maps, glowing portraits that show where energy escapes from the surface. These maps reveal something astonishing. Io gives off more than 10 times as much heat as Earth's moon. Nearly all of this heat comes from tidal forces, the endless kneading of Io's interior by Jupiter's gravity. But the heat is not spread evenly. Some areas leak much more energy than others, even in regions where eruptions are rare. This uneven pattern tells a deeper story. It suggests that Io's crust is not uniform. Some parts are thick and strong, others thin and weak. Beneath the surface, rivers of molten rock may be moving through secret channels, feeding volcanoes in some places while bypassing others. There could even be underground lakes of magma, glowing seas of molten sulfur and rock waiting beneath the crust. Some scientists think that Io's outer shell, called the lithosphere, floats over a softer, more flexible layer of heated rock. This strange structure allows heat to travel sideways beneath the surface before finding weak spots to escape. In this restless world, the crust behaves like a patchwork quilt. Old vents close as new ones open. Lava cools, hardens, and then breaks again somewhere else. Over time, the moon's surface is constantly renewed. Even when there is no eruption in sight, Io seems alive, shifting, breathing, and glowing beneath its skin of stone. Scientists dream of sending a lander equipped with a heat probe to touch the ground and measure the warmth directly beneath the surface. An orbiter fitted with sharper infrared eyes could watch the changes in real time, following the flicker of hotspots as they brighten and fade. Even higher resolution cameras could reveal tiny cracks, fresh vents, or bulging domes where molten rock is gathering. But until such missions are possible, the thermal maps remain our best window into Io's secret heart, a world that glows from within, restless and alive with energy that refuses to rest. And then there are the Plumes, the fiery towers that make Io unlike any other place in the solar system. Imagine fountains of gas and dust shooting hundreds of kilometers into space, far higher than anything Earth has ever seen. These are not gentle eruptions. They are pillars of fire so powerful that they fling material beyond the curve of the moon itself, tracing great arcs across the sky before falling back as dark rings upon the surface. The first time humanity witnessed such a sight was in the year 1979, when NASA's Voyager spacecraft flew past Jupiter. To the astonishment of everyone watching, the cameras caught what looked like a volcanic fountain leaping from Io's surface, a plume nearly 300 kilometers tall. No one had imagined such explosive power on a distant, airless moon. That discovery changed how scientists thought about volcanic activity across the solar system. Since then, many more plumes have been seen, each revealing new details about Io's fiery heart. On Earth, volcanoes must fight against the atmosphere. As magma rises, it releases gases like water vapor, carbon dioxide, and sulfur dioxide. These gases expand and push the molten rock upward, but they meet resistance from the thick air above. The eruption slows and the ash spreads out into clouds. On Io, things are very different. Its atmosphere is so thin, less than 1/billionth the pressure of Earth's, that there is almost no resistance at all. When gas explodes from an underground vent, nothing holds it back. It bursts into space with breathtaking force, carrying dust, ash, and bits of frozen sulfur high above the ground. Scientists have grouped Io's plumes into two main kinds. The first are called Prometheus-type plumes. These tend to be lower, usually under 100 kilometers tall. They happen when hot lava flows across the icy plains of frozen sulfur dioxide. The heat flashes the frozen gas into vapor, causing it to burst upward in a violent jet that carries particles with it. It is almost like a chain reaction, lava touching frost, turning it instantly into an explosion of steam and dust. These plumes can last for long periods as lava continues to creep across the ground. The second type is far more dramatic, the Pele-type plume. named after one of Io's most powerful volcanoes. These eruptions come directly from deep underground, where gas-rich magma surges through cracks in the crust. When the pressure builds too high, the vent splits open, and a huge burst of gas and molten sulfur is released. The eruption shoots upward like a cannon blast, forming a vast umbrella-shaped cloud that spreads out before falling back to the surface in wide rings of ash and frost. These eruptions are shorter but far taller, breathtaking towers of fire that can stretch several hundred kilometers into space. For comparison, one of Earth's largest volcanic eruptions, Mount Pinatubo in the year 1991, sent ash about 35 kilometers into the air. That eruption was so powerful it cooled Earth's climate for years. But on Io, eruptions almost 10 times taller happen regularly. Because there is no air pressure to slow them down, the ejected material follows pure arcs, like stones thrown in slow motion, and with Io's weaker gravity, these arcs reach far and wide, raining volcanic debris over regions hundreds of kilometers away. Across Io's restless surface, the evidence of its volcanic fury can be seen in sweeping patterns that stretch for hundreds of kilometers. When its explosive plumes shoot high into the thin space above the moon, some of the particles fall back down far from their source, creating dark circular stains that mark the outer edges of ancient eruptions. These dark rings are like fingerprints left behind by mighty blasts long past, each one telling a story of heat, pressure, and movement deep within the moon. Modern technology has given scientists powerful tools to study these plumes in detail. Using thermal and optical imaging, along with high-speed cameras and special filters sensitive to different wavelengths of light, researchers can see gases glowing at a wide range of temperatures and compositions. Some plumes shimmer in visible light, while others glow in ultraviolet or infrared, invisible to the human eye but vivid through scientific instruments. Through these colourful signals, scientists have learned that the plumes are made mostly of sulfur dioxide gas, mixed with tiny grains of sulfur, sodium, and volcanic dust. Sometimes, around the biggest and brightest plumes, glowing arcs appear, shining like ghostly halos. These are made of sodium atoms that have been ionized by sunlight, glowing brilliantly like neon signs floating in space. Such eruptions do more than decorate the moon's skies. They actively reshape Io's surface and even affect the space around Jupiter itself. When the fine particles from these eruptions fall back down, they coat the surface in fresh, thin layers of frost and dust. Over time, this continuous sprinkling covers old features, erasing the scars of previous eruptions and giving Io a surface that is always being renewed. But not all the debris returns. Some fragments escape Io's gravity entirely, drifting into orbit around Jupiter. These lost particles become part of a vast ring of charged gas known as the plasma torus, a glowing belt that wraps around the giant planet. Other particles take a more dramatic journey. Guided by Jupiter's powerful magnetic field, they spiral along invisible lines until they crash into the planet's upper atmosphere at tremendous speeds, creating spectacular auroras that dance across Jupiter's poles. In this way, Io's eruptions light up not only its own surface, but also the skies of the largest planet in the solar system. Each plume holds valuable clues about what is happening beneath Io's crust. Its height and shape tell scientists how much gas was trapped, how fast it was released, and how deep the molten rock was when the pressure began to build. In a sense, the plumes act like pressure valves, venting the moon's inner energy before it becomes too great. Yet, not every eruption comes from a towering volcano. Some plumes rise mysteriously from flat plains where no visible vent or mountain exists. These hidden, or stealth, eruptions may come from underground chambers that have not yet broken the surface, or from molten lava that moves silently below a hard crust of rock. Even so, their effects are massive enough to be seen from Earth. When Io passes in front of Jupiter, powerful telescopes on Earth can sometimes spot the shadows of these plumes on the planet's bright face. They appear as faint dark smudges beside the moon, revealing both the size and reach of the eruptions. By carefully studying their colour and brightness, astronomers can even estimate a plume's composition and how high it soars above Io's surface. On Earth, volcanic heat finds its way out slowly through processes like plate tectonics and the slow spreading of the ocean floor. Io, however, releases its energy in violent, dramatic bursts. Each plume is a message from within, a sign that the pressure below has built up until the moon can no longer contain it. When the gas finally breaks free, the surface shakes, cracks, and reshapes itself. In the future, spacecraft may one day fly directly through these plumes, collecting samples of their gas and dust to study Io's chemistry up close. For now, scientists can only watch from afar, tracking each fiery eruption as it bursts upward into the cold, empty darkness of space. Over the years, researchers studying Io have developed their own unique language to describe its remarkable volcanic landscape. Common words like volcano and crater are not always enough to capture what they see. Instead, they use special terms such as patera, flow field, and caldera collapse, expressions that describe features found nowhere else quite like on Io. A patera may look at first like a crater, a round or oval depression in the ground that can be dozens or even hundreds of kilometers across. But unlike impact craters made by falling meteors, paterae are born of fire, not collision. Their rims are irregular and rugged, their floors often sunk deep below the surrounding terrain, sometimes filled with shimmering pools of lava still glowing from recent eruptions. These are not scars from rocks falling from the sky. They are marks carved by Io's own volcanic heart. One of the most famous paterae is Loki Patera, a gigantic volcanic depression shaped more like a horseshoe than a circle. Loki is the largest and most powerful volcanic feature on Io, and one of the most active volcanoes in the entire solar system. Stretching for more than 200 kilometers across, it regularly brightens and dims as waves of fresh lava overturn its surface in fiery cycles. Across Io, there are more than 400 paterae, each with its own unique shape and story. Some have steep bowl-like sides, others are wide and shallow, spreading over plains of hardened lava. Some form when molten rock beneath the crust swells upward and then collapses as the pressure drops. Others are created when lava melts the rock beneath it, leaving behind hollow spaces that eventually cave in. Every patera is a wound, a visible reminder of the forces that constantly rebuild the moon from within. Flowing out from these depressions are the flows, long fiery rivers of lava that stretch for great distances, winding across Io's plains like glowing threads. They move, cool, and solidify, forming new surfaces that will soon be covered again by the next eruption. On Io, nothing stays still for long. The moon is alive with motion, its surface forever reshaped by the powerful energy locked inside it. On our planet Earth, rivers of lava can stretch for many kilometers, flowing slowly across the land before cooling into solid rock. But on Io, one of Jupiter's fiery moons, these molten rivers go much, much farther. Some of the longest lava flows ever seen in the entire solar system are found there, reaching lengths of up to 500 kilometers. To imagine that distance, think of a glowing river of lava stretching all the way from New York City to Washington, D.C. These lava streams are not sluggish or gentle. Some of them race across Io's surface in only a few days, or even just a few hours. They rush through deep channels, spill over cliffs, and flood into wide, low-lying plains. The face of the moon changes almost overnight, reshaped by the unstoppable movement of molten rock. Such speed and distance would be impossible on Earth, and the reason lies in the nature of Io's lava itself. Unlike the basaltic lava that flows in places like Hawaii, Io's lava is made of a different, more extreme material called ultramafic rock, which is rich in metals like magnesium and iron. This kind of lava burns incredibly hot, reaching temperatures of more than 1,600 degrees Celsius. That is several hundred degrees hotter than any lava found on Earth. Because it is so hot and fluid, it stays molten for longer and can travel much farther before cooling. Across Io's surface, scientists have seen entire regions flooded by these fiery flows. New lava spreads over old plains, filling cracks, covering ancient crater floors, and creating vast glowing fields. At the edges of some of these flows there are bright hot spots where fresh lava keeps breaking through, feeding the rivers of fire from below. Over time, some older flows get coated with sulfur frost, giving them a pale yellowish look, while others turn dark and black, signs of recent heating or fresh eruptions. Seen from orbit, these colourful scars tell a vivid story of endless renewal. Another striking feature of Io's landscape is the caldera collapse. On Earth, this happens when a volcano empties its magma chamber during an eruption, and the land above suddenly caves in, forming a deep circular depression. But Io takes this to a whole new scale. While most calderas on Earth are only a few kilometers wide, some of Io's can stretch for more than 100 kilometers, giant sunken basins surrounded by towering cliffs. These collapses happen when underground magma drains away too quickly, leaving a hollow space beneath the surface. With nothing left to hold it up, the crust gives way, and the ground drops suddenly, creating a huge pit-like formation. Unlike Earth, Io has no rain, wind, or atmosphere to wear these cliffs down. The airless silence keeps every edge sharp and fresh. Once a caldera forms, it stays exactly as it is until it is buried by newer eruptions. Some calderas hold shimmering lava lakes that glow in the darkness, while others are empty, dusty basins waiting for the next surge of molten rock. On Io, everything is connected. Lava flows, Patera and Calderas often interact in dramatic ways. A lava flow might begin inside a Patera, a type of volcanic depression, burst from a vent at its edge, and spread across the plains. After the eruption, the ground above the drained chamber may collapse, turning the Patera into a caldera. Then, as hot gases escape from the newly exposed lava, they can form a towering plume that rises high into space. Each event flows into the next, linking eruption, collapse, and plume in one continuous cycle of fiery transformation. The number of these volcanic features is astonishing. Even though Earth is filled with volcanoes on land and under the sea, Io has far more active sites of eruption. Almost every part of its surface shows signs of fire and renewal. Images from spacecraft and telescopes reveal that nearly every square kilometre of Io has been melted, cracked, or buried at least once. It is a world in constant motion, a restless living landscape of heat and chaos.